So today what I'm going to go over is how to perform an EFA in R. So this is a class example from my structural equation modeling class, getting people ready to talk about SEM and CFAs. Sometimes it's easier to start with an EFA. And so what I did was I took a student project where they collected data on a bunch of different political ideas, and then also collected data on the openness to experience scale. Okay, so this scale has 20 questions, and people answer from very inaccurate to very accurate, so it's a 5-point Likert scale, and it has a bunch of sort of odd questions on it, mostly about art and different ideas, and so we're going to see if we can figure out what kind of factor structure that scale has. Okay, so the point of EFA is to really look at do the questions load together? Is it like a theoretical structure? And so we're just going to kind of see what happens when we let these questions do what they want. Because then when you get into confirmatory factor analysis, that's when you force the questions to load on specific subscales and see if it still works. So it's kind of a two-part system if you're doing a scale development kind of paper. And so what I had them do for the assignment is pretty simple. And so we're going to copy that. Come over here to RStudio and see if we can go through each one of these points and work the assignment. So make this a little bigger. There we go. All right, so I'm going to use Studio for R because it's fantastic and I love it. And what we're going to do is create a R script that runs all of our code and handles the EFA for us. Okay, so the very first thing you have to do is import the data set. So let me import the EFA data. So I'm going to use import data set over here from text file. I gotta find it. Let's see. Doing class assignments in R. And so we're doing EFA data. Open. So the first thing I'm going to do is I'm going to rename this to something easier to type, like data. And you'll notice down here in the output window, essentially, where it tells you the data frame, it hasn't really figured out that those, the top line is my header. So what I'm going to do is say, yes, it has a header, so it comes in with these nice labels, 01, 02, 03, and then I can change some of these other options too, but I'm leaving them alone. So let's hit import. So I'm going to copy that line of code so I don't have to figure out what the file path is, and now I have my data set imported. Okay, so I have 99 observations, so not quite enough for EFA, but this is an example. It would be better if I had more. And then I've got a bunch of different, my 20 questions and a condition variable. So that's the first thing, I have the data. So let's save this thing. Alright, so this is the EFA example. Okay, so the nn.r. Alright, there we go. So the next thing it wants me to do is do some data screening. So let's see. A short kind of data screening. So first thing I want to do is exclude all the missing values from the data set. Well, that's pretty easy. Let's call this no missing. Let's na.omit. Will omit all people who have at least one NA. So it omits the entire row. And I want to do that on my data. And so I can create a new data set called no missing that has excluded everyone that has got missing cases. That's probably like the quickest way to get rid of missing values. Now if this were a real study I was working on, I would go through and look at what type of missing data they are. So they completely at random or not at random. And then I might impute some of the data using maybe the mice library. Alright, so I've excluded the missing data values. And then the last thing I want to do is drop this condition column. Because I'm doing EFA and I don't need the condition. That was for maybe an ANOVA. And so I just want to make sure that this gets excluded, makes it a little easier to use. So let's call this the final data set, if you will. And what I'm going to do is say, I want my no missing data set, so this is subsetting, and I want all rows, so I'm going to leave the first thing blank, and I want to take out the last column. So I know there are 21 columns, so I could just do minus 21, But what I could also do is, if I can't remember or figure out how many columns there are, is tell it to take out the last column by doing minus and then in col, I think is what it is, and then the data set name again, no missing. Because in col, right, should tell me how many columns there are. Let's check. Right, so there's 21 columns. So I've told it to give me all the columns minus number 21. Let's see if that works. Right, so my final data set looks like it has 20 variables, and with only that last column is gone. See, my no missing one still has that condition one. So I've made new data sets each time to kind of keep it straight for me what I'm doing, but you could keep just editing the original data set, because if you mess something up, you can reload it. All right, so we've done B here. So the next step is the actual EFA. So we're going to run this EFA on this openness to experience scale, and let's start with our number of factors. All right, so let's do the parallel analysis first. So parallel analysis will tell you how many factors are greater than chance. And the first thing we're really going to need to be able to run any of this is to use two packages. So let's load those packages first. And the first one is the Psych Package. It's a really great package for psychologists and other people who are interested in experimental research. It's got lots of cool data screening functions and lots of EFA and things that you might use, ANOVAs, if you were in the psych field. All right, we're also going to load GPArotation, which is a required package to do some of these analyses. All right, so I've loaded both of those. It's grumpy because I haven't updated R. Okay. So parallel analysis. So how many factors are there? So I'm going to save this as parallel. Okay. Parallel. Let's try again. And parallel. So not known for my spelling. However you spell it. And I think it's with the E's. Let's make it right. There we go. The function is fa.parallel, and this is why I can figure out how it's spelled, because they spelled it correctly. And so the way fa.parallel works is that you need the data frame that you're going to run an EFA on, but no extra variables. So you don't want to include that condition variable, because it'll get analyzed and you don't want to do that. Okay? So I'm going to call this, what did I call it? Final data set. Okay? And then you want to tell it kind of what you're going to run. So FM equals, we're going to say ML, so that will run maximum likelihood math. So the way I think about that is factor math. So what options do I have? You have MinRes, I think, is the default, and then you'll have things that are things like weighted least squares and unweighted least squares, generalized least squares. So there's PCA, a couple different options. Right? And then the next thing you'll do is FA equals FA. So what type of factor analysis? You can do factor analysis, PCA, or both. Okay, so if you don't tell it to give you any particular one, it will do both for you. So let's run that. All right. Okay, so I saved it so I could save the Eigen Values, and that way it will give me the opportunity to look at it. And but the first thing that happens is it automatically gives you this plot. So let's make the plot a little bigger so you can see it better. And so what happens is the parallel analysis will show you your actual data. That's in blue here. So those are my Eigen Values, and they're plotted. This is a scree plot. And then it shows you the simulated data and the resampled data. And I'm pretty sure you don't see the second line because they're right on top of each other. And so there's actually two lines here. And so what you can get is the point of inflection. So where the two lines start to cross, it means that or like kind of where it stops being dropping and is starting to be a linear line. And the best way I can explain that is, like, if you look here at number 3, it starts to even out and become a nice, the distance between each one is about the same. And then if you're looking here at 1 and 2, there are big drops between them. So I've always looked for the largest drop when it stops being a large drop. So I would say this is 2. But some people call this the point of inflection, where essentially the simulated data and the actual data sort of meet. And so that would be 2 here as well. But just in case you weren't sure, it draws you a nice pretty line across, and you look at how many of them are above that line. So there are 2 eigenvalues above that. So I would say that this, for how many factors does a parallel analysis indicate, I would say 2. Okay. All right. Let's see. My scree plot here. Well, I'm sorry. I actually did the scree plot first. So let me change this real quick. The parallel analysis probably indicates 2 as well, but I actually haven't looked at what it says, and that's down here in my console window. So it actually says 3. And so while the scree plot looks like 2, the parallel analysis says 3. It is not unusual for them to disagree. So let's look at one more rule. Now this rule isn't super popular. It used to be called the Kaiser Criterion, and it kind of depends on the day if it's using Eigen Values over 1 or Eigen Values over 0.7. That's sort of the 2 different rules. But the reason I saved this analysis was to be able to look at these. Okay, so I'm going to do FA.values. Okay. Oh, I typed that in the wrong window, sorry. So what you do to look at your eigenvalues is you do the name of what you saved it as. So I saved it as parallel. And then there's an option here for FA.values, and that tells you what the actual eigenvalues are. So it's a vector of eigenvalues. And then I would just count the number of ones that are over 1 is 2. And then the other rule is over 0.7, that's actually 3. Okay, and then I'm just counting. 1, 2, and then 1, 2, 3. Now, what I have is I have 2 different options here. I could run this as 2 factors, because there are 2 indicators for 2, and I could run this as 3 factors, because there's 2 indicators for 3. And you would just kind of have to say which theoretically makes more sense. I'm going to go with the simplest is better, so I'm going to try 2. And if I were doing this for real analysis, I would try 2 and 3 and see what happens. But if my theory said it was 2, I would probably go with that more than this parallel analysis, because generally we're trying to see if our theories match what the data is. But you can always try both and compare them to each other. All right, next step is simple structure. So I want to run this with an Eigen rotation and maximum likelihood as the type of math. And so an Eigen rotation is an oblique rotation, so it'll allow the factors to be correlated. And when you work with people, generally you feel like the factors are correlated, so that's kind of a normal thing to use. So I'm going to save this. Let's say it's 2 factor. And what you do is FA for factor analysis, so that'll give you the function for factor analysis. And then you want to put in the data set name, so the last data set we have is final here. And then you want to do in factors equals, and I got 2, rotate equals, and this has to be in quotes, Eigen, okay, because it's text. And then FM equals ML. So that setup will run a factor analysis on my final data set with only 20 variables for 2 factors with an Eigen rotation and maximum likelihood math. Right. So I have run the first round of simple structure. So since I saved it, it doesn't print out, so let me tell it to print out down here for me. It gives you a bunch of stuff, but let me scroll up to the top here. It tells you the factor analysis method is ML, so for math. It tells me how I called it. And then it gives me the standardized loadings, which is what we want. Okay. I have a hard time seeing this sometimes, but basically what it does is it gives you factor 1, factor 2, and it names them before it starts to rotate them, and so sometimes they'll flip depending on how much variance they have. So the second factor actually ended up having more variance, which is okay. H2 is the kind of like R squared, so how much the variable is accounted for across all factors. And then U2 is uniqueness, so it's how much is unique. So you got communality and uniqueness. The last thing it gives you in this particular package is item complexity. What we're going to use is just look at the loadings right now. So I'm going to cut and paste this into Word because it always seems a little easier to work with in Excel or Word than the console window. And that's just so I can see it a little better. So in this first line, I want to look for questions that don't load or double load. So loading, remember, is 0.3. It can be negative. So this first question is fine because it loads on one and only one factor, that second one. Second one's fine. That third one, so 03, is no good. It doesn't load on either factor. If you look at its communality, it's really low. Fourth one's fine, fifth one's fine, 6, 7, 8, 9, 10. Okay, 11 is bad because it loads on 2 of the factors. 15 because it doesn't load on anything. 16 because it loads on both. And then that's it. So what we're going to do is run this whole thing again, the same code, without those questions. So I'm going to copy this line, and I'm going to call this round 2. And I'm going to take out some of those columns. So remember the subsetting rules. So I want to do all rows, and then I want to take out a subsetted number of columns. So 03 is going to be column 3, 11, 15, and 16. So this is why it's really great to, one, have your questions in order, and then not have anything else in the data set. So you aren't constantly having to subset it, but now that I know these questions are bad, it makes it really easy to take them out. So let's run that one. Let's see what that output looks like. Scroll up. So let me look at the loadings here. All right, so one at a time. 1 is good, 2 is good, 3, oh, that's 4. So I'm scrolling through them one at a time, looking. And that looks to me like we've achieved simple structure. So simple structure is where it's one and only one loading. And so it doesn't double load across multiple factors, and it doesn't not load on anything. So this would be what I would consider simple structure. All right, so we've run the analysis excluding questions that didn't load. The next question is, while I have simple structure, is that model adequate? So does it work, basically? So I want to look at my fit indices. So that's going to be my output here. Scroll down a little bit more. Item complexity, yada, yada, yada. There's chi-square. So here's root mean square of the residuals. So that's 0.08. So we got RMSR is 0.08. And that is in the good or adequate range. Let's do the RIMC now. So I'm going to scroll down a little more. Let's find that bad boy. Here's the RIMC index here. So I got 0.094 and the 90% confidence interval. Okay. And that's in the okay range. So less than 0.10 is considered adequate. It means barely publishable, generally. Okay. So TLI, so the Tucker-Lewis index, so this one should be high. It's right here. Tucker-Lewis index is 0.83. And then one of the main problems I have with this particular package is that generally CFI, or the wow, just jumped out of my head. One of the other big fit indexes, comparative fit index, sorry, I had a moment there, is not included in this output. And that is generally something I see reported with a lot of EFAs and structural equation models. So we're going to calculate the CFI. Now, the way to do that is a little hairy, but I'll walk you through it. So it's 1 minus, and then we're going to do 2 parentheses here to get started. So you're going to use the name of the last save. So it's 2 factor, 2. And we're going to pull something out of that. So it's a list, so I can pull statistics out of it. And that is statistic, all in cap. Okay? That's chi-square. Okay? So we're going to take chi-square minus the same 2 factor 2. And I'll pull something else out of that. So chi-square minus degrees of freedom. And so all of that's for your model. So it's chi-square minus degrees of freedom divided by the null model's chi-square divided by degrees of freedom. So 2 factor 2, and let's see here, it's null dot chi-square, there it goes, minus, oops, I'll get my parentheses going here, 2 factor 2, and we need the null degrees of freedom, there we go. So what that does is it takes the chi-square for your model minus the degrees of freedom for your model, subtracting the null chi-square minus the degrees of freedom for your model, and divides them out, and then it's 1 minus that. Okay? Now all of that information is in here, but it's not always totally obvious what it is, and so I found it a little easier to just tell R to calculate for me, because sometimes math, not my strong suit. So let's run that. And the way that you know you've probably done it at least close to right is it should be slightly higher than the TLI. So one of the things about the CFI and the TLI is they're usually pretty close, but CFI is usually a little higher until they top out at the top. So I got 0.88. Now both of these are in the sad face blah region. Okay. So neither of those are good because you want them to be over 0.9. Alright, so I've got 2 indicators that are okay and 2 indicators that are like, not so okay. So maybe this, even though I can achieve simple structure, maybe this scale isn't so good. Now really one of the big problems that we have is that we just don't have enough people. 91 is hard to estimate on. Okay. So it would be better if I collected more data. So let's do reliability. Now base R comes with, or maybe it's in Psych. I think it's, let's see. Oh, no, this is in Psych, an alpha, which calculates Chromebox alpha. That's actually a bunch of different types of alpha that are included, but we're going to do Chromebox alpha. And what you have to do here is pick the questions on where they load. So what I need to do is go back to my loadings, and let's create a list of loadings for each one. So factor 1 here is going to be number 1, right? Number 2, 12. Okay, I can't remember that many in my head. 1, 2, 12. So I'm looking for where the loadings are over 0.3. I actually did this for ML1. Okay, it's 14 and 18. Doesn't really matter what order you do them in, because we're going to give them names here in a minute. So this should be all of the other ones. We have 4, 5, 6, 7, 8, 9, 10, 13, 17, 19, and 20. And I'm going to take that and use that to subset the data. So for my alpha, I'm going to do this in my final data set. I'm going to subset the data, so I'm going to go all rows and give me just these columns. So that's going to give me reliability for all rows and just those columns. Let's do that same thing for the second one. Because you don't want to calculate reliability overall because you excluded some questions and then you want it by factor. Oops, lowercase c here. There we go. Here are all my second questions. All right, so let's see. Reliability for the first one. Okay. Oh, maybe we didn't reverse code some items. That would definitely affect our statistics. It would be very grumpy, so that's maybe one thing to check. And so once you get that reliability calculated, you can look here. It says raw alpha is 0.85, or you can look at the 95% confidence interval. So the alpha for one of our factors is in an appropriate range. Over 0.7 or 0.8 is usually considered pretty good. And so I would say that scale is pretty reliable, even though the fit for the factor analysis is not so good. Let's do the second one here. And let's see, the alpha is 0.82. And so that's pretty good as well. So we've got 0.85 for factor 1, 0.82 for factor 2. Great. Now the last thing is a theoretical question. So this is where I would look at what the questions are and how they relate to maybe what I would think theory-wise. Okay, so let me go back to my document here and make it a little bigger for you guys to see. So I'm working on, let's see, 1, 2, 12, 14, and 18. So looking here, I have art, vivid imagination, do not like art. Wait, 14, 1, 2, 12, yeah, 14, do not like art museums, and 18, too much tax money to us artists. Okay, so this is clearly about the arts. So that first factor is all about art. Okay. Now our second factor looks like it's 4 through 10, 13, 17, 19, and 20. So let's see. Conversations at a higher level, new ideas, thinking about things, can say things beautifully, new ideas, vocabulary. So this seems to be very related to like literature, thinking about abstract things. 13, so a reverse question, philosophical discussion. 17, deeper meaning, theoretical discussions, and abstract ideas. So I would say this one's more your like thinking, philosophy. And so you would label those based on some, usually the questions are created based on some theory that you might have. Alright, so that's how you do an EFA in R using kind of a 3-step procedure. We talk about what are the number of factors that you should run, can you achieve simple structure, and is that simple structure adequate? Can you explain it? How does the model fit? What I would do next if I were doing this for a research paper is try a 3-factor model and see if my fit indices are better for a 3-factor model.